So let's do an overview of the electromagnetic accelerator. So the first thing that you can actually see starting at the front, each of these little sections are actually epoxied coils of wire. So there's going to be a wire that's wrapped around many times, and then I've put epoxy that's ferromagnetic around it, along with toroids from a transformer, and that should help conduct the magnetic field within the coil. The power is actually gained when the projectile is changing the inductance of the coil. So if it's a really high inductance coil, for instance if it's heavily shielded with ferromagnetic material, then it's going to pull extra hard because there's going to be a lot of change in inductance. So that's why you'll see that these are really tightly wrapped rather than having just the wire exposed on the outside. The tube itself is actually infrared see-through. This makes putting sensors on it a lot more straightforward. If that wasn't the case, you'll have to drill into the tube and then put some sort of reflector or see-through on it, and those are really hard to get aligned. So if you can get something that's see-through in the spectrum of your sensors, that's the way to go. So these first two sensors are actually not used for anything other than sensing the velocity of the projectile as it's leaving. So they should be exactly 18 centimeters apart. So when a projectile is fired, it's already reached maximum velocity by the time it gets to those, and that's how I can measure it. So when you see, for instance, that I'm giving a metric like 2.5 milliseconds, it's 2.5 milliseconds from when this one sees it to when that one sees it. And that number in particular corresponds to 70 meters per second. So these two guys would normally be plugged into a power supply and then plugged into my triggering oscilloscope in order to get them to work. Moving down the line to the really complicated part, each of these is a high power SCR. They're rated to a couple thousand amps, about 1,000 volts or thereabouts. And I know that they must be relatively near their tolerances because there was a similar part that had similar specs but was in a TO220 package, I believe, which is the kind of like flat transistor rather than like the bolt style. And those guys were burning out even though they were supposed to be rated for the same thing. So I'm probably pushing, in the high kilowatts, tens, hundreds of kilowatts sort of range when I fire these guys. You can see on the far side are the capacitors. This design actually has a capacitor for every single one of those SCRs. So what will happen is when the computer decides that it's time to fire this SCR, that guy will turn on and drain just its capacitor. It won't drain any of the others. And in that way we can start at the beginning firing this one, this one, this one, and so on all the way down the line. You can also see that each of these capacitors has a associated sensor. The sensor does not determine exactly when it fires. That's still a decision that has to be made by the computer. Because even when the sensor sees it, that doesn't mean that it's time to fire because there's a lot of complexity and ramp up and cool down times on coils. You can also see that each of these sensors actually has a shielded wire on it. I had a lot of problems with electromagnetic noise. That's in retrospect to be expected when you've got such high power pulsing. I assume that because they're inductive coils, there would be like a certain degree of ramp up and it wouldn't make that much EM noise. You can see that each SCR is actually held in there with a bracket. Those guys came off the 3D printer. Again, that device is invaluable when creating things at home. So if you want, for instance, this bracket to be different than that bracket, you can make them that way. You just change the specs on the 3D printer, you get a totally different world. You'll also notice that actually the swivel mount that I've got on this thing is 3D printed in 3 different pieces. There's a lot of wire on it because I actually don't totally trust the mount. The gun itself is actually real heavy, and because of that weight, I'm concerned that the mount, well, the short answer is if you work on something for long enough, you don't want it to fall off your tripod and hit the floor and destroy itself. So continuing to move down the line, what we've actually got here is the main control panel. So the top one is going to indicate what your current battery voltage is. The bottom one's going to indicate what your capacitor power is, or your capacitor voltage. So if I switch those guys on right now, I can see that the computer powers up. I can see that I'm getting readings off of these two. So the battery pack's reading 27.7 volts, capacitors are on empty. The other controls we've got This is actually, I think that's a switch that turns off the display, so if you're trying to use it and not have it make any light or give yourself away, that switch will do it. That guy indicates whether there's power on the capacitors. You can see that there's just like the slightest little glows of red right around there. That means the capacitors are really close to empty, which is about where you'd expect them to be, given that I haven't been charging it and firing it right now. If you hit that button and those lights light up in a bright way, that means the device isn't safe to work on, or rather that it's probably safe to fire. We've got the main computer, which is actually a 16, I think, megahertz chip, and it's just running a really basic C program, but what it gets to do is you can see a lot of wires coming into it. It's taking inputs from all of these sensors, and when it makes a decision about what to fire, it's feeding that into these firing circuits. So each one of these guys is actually assigned to one of the capacitors. And their job is to, as soon as they see a signal, turn that capacitor on and get it going. One complexity of this problem, though, is that because of the electromagnetic noise from firing, and especially because of the electromagnetic noise from charging is actually very brutal on this machine. I've had a lot of problems with pre-firing while charging. So there's actually, this wire is coming out from where it knows there's a charging signal, and it's specifically blocking the act of charging. So if the machine is in charge mode, it will know to ignore any signals it's getting on these sensors because those signals are probably wrong. Moving around to seeing the innards of our machine a little bit more, you can see that there's a main battery pack here. That's what this whole thing is running off of. This is an inductor used by the charger, and that inside there is the charger. So it's a variable frequency charger of my own design. I wasn't able to find one that I could buy on the internet that looked any good. So for instance, a lot of the chargers that you'll see are, you know, they might be like some sort of stepping charger where they have more than one transformer coil and they'll flip between them. Or you'll see, for instance, chargers that are constant frequency and just take fucking forever to charge a big capacitor bank. So I actually built one myself that's variable frequency, and it's been working pretty well for me. Way up at the front there, you can actually see the triggering assembly. So the bottom one is the charge button. When you press it, the machine starts charging. It actually does have a cutoff itself, and it knows when it's reached its maximum charge. And then I've got a very light pressure switch to actually fire. So that's kind of the rundown. You'll notice a lot of this stuff is really, for lack of a better word, half-assed, but that makes it extremely maintainable. So you could say that you're going to make, for instance, a really compact and exacting control panel, or a really compact and exacting computer system, but then when you realize that you need to change that because what you came up with doesn't work, or if you want to upgrade the machine, those things aren't just aren't going to fly. And frankly, it's not the kind of device you're going to take off and run with, so you might as well make it easy to work on. And that's kind of the overview of the machine that I've got here. I hope that makes sense. And I'll probably be making another video of it firing in just a little bit.